Logs and indices, logs type 5, ln. So up until this point we've seen equations like 2 to the x equals 8, where we're looking to solve for x. And they've been quite easy to solve because we were able to take both sides to the same base. In other words, we can say that 8 can be written as base 2 to the power of 3. And then we were able to equate the powers because the base on both sides was the same, which then gave us x equals 3. So in these examples today that we're going to be looking at, we're not actually going to be able to take both sides to the same base. So we need to apply our log rules instead to help us solve for the unknown variable power. So say, for example, we have a question like this, where we have 2 to the power of n equals 31, and we're asked to solve for n. And what we note then is that we can't write 31 as base 2. So there is no power of 2 that will give us an answer of 31. So because we can't raise both sides to a power with the same base, the process of solving for this unknown power is to get the log of both sides. Now you can get log to any base of both sides, but for the purpose of all of our questions, I'm going to use the natural log. And this is going to come in very handy when we're looking at real-world applications of log equations. So I'm going to stick to the same principle every time. So like anything in maths, if I do something to one side, I must do it to both sides. So if we look at 2 to the n equals 31, I'm going to get log of both sides. That means I'm going to say natural log of 2 to the n equals natural log of 31. And I know from my log rules on page 21, if I zoom in here, that if we look at the third rule down, if I have anything raised to a power, then that power can come down in front of the log. So by doing that, we can find our unknown variable because the power here is n. So by bringing down the n in front of our natural log of 2, I'm now going to have a way of evaluating for n because I can divide across by natural log of 2 on both sides, which gives me n on the left, and natural log of 31 divided by natural log of 2 on the right-hand side. So now all I have to do is go to my calculator, making sure we're pressing the natural log button on your calculator. And if we input that into our calculator, we're going to get a decimal answer. So in the leave insert, we'd be asked to find a corrected so many decimal places or so many significant figures. So for the purpose of this example, we're going to get our answer corrected 2 decimal places. And that gives us n is equal to 4.95. So a very useful application of our log rules. So let's have a look at another example. So here we have 2 terms on each side of the equation that both have an n in it. So again, what I'm going to do is get log of both sides. So we have natural log of 5 to the power of 2n minus 1 equals natural log of 4 to the power of n plus 1. So again, applying that same rule of bringing down the power from page 21 in our tables. That means that if I bring down the power, I make sure I use brackets because there's 2 terms in the power. So in other words, I'm bringing down 2n minus 1. So that'll be times natural log of 5. And on the right-hand side, I have to bring down the power, which is n plus 1. So again, I'm putting it in brackets, times natural log of 4. So I'm going to have to multiply out the brackets on the left-hand side there. So we have 2n times natural log of 5 minus natural log of 5 times 1, n times natural log of 4, and then 1 times natural log of 4. So I'm going to have to bring anything with an n to the left-hand side and everything else to the right-hand side. So on the left, I have 2n natural log of 5, so I'm going to keep that on the left-hand side. And then I have a minus natural log of 5, so I'm going to bring that to the right-hand side. I have an n natural log of 4 on the right-hand side, so I'm going to subtract that from both sides, which gives me minus n natural log of 4 and plus natural log of 4. So there's no n coefficient there. So now on the left, I have an n and an n. So I'm going to take out the highest common factor on the left-hand side, which gives me 2 natural log of 5 minus natural log of 4. And on the right-hand side, I just have natural log of 5 and natural log of 4. I cannot add them, they are not like terms, okay? So we have to do that all on our calculator. So on the left-hand side now, I want to have n on its own, which means I must divide both sides by this term here. So if I divide the left by 2 natural log of 5 minus natural log of 4, I'm left with n. And then I must do the same to the right-hand side. So I'll be dividing natural log of 5 plus natural log of 4 by 2 natural log of 5 minus natural log of 4. And then all we have to do is sub that into our calculator using our natural log button and our fraction button. And again, if we get our answer correct to 2 decimal places, that gives us a value of 1.63. So again, be careful when you're inputting your values that you're using your fraction button there and your natural log button. Okay, so let's look at another example. So again, here I'm asked to solve for x, given that e to the power of 2x equals 3. So again, we note I clearly can't write both sides to the base e. So I'm going to get natural log of both sides. Bring down my power using my log rules on page 21. And this time we're left with something really nice. We're left with natural log of e. So you might remember in class that we were saying natural log is basically log to the base e. So that's log e to the base e. And again, any log of any number to the same base is always 1. So that's a nice one that comes up a lot. So again, if we go back to our log rules and we see this one here, log of any base to the same base equals x, because obviously if I bring down the power of x, I have x times 1. So that leaves us then with 2x times 1 equals natural log of 3, and therefore x equals natural log of 3 divided by 2. So again, using our calculators, and we get our answer correct at 2 decimal places, we get x equals 0.55. So for all these examples, I've gotten my answers correct to 2 decimal place. But again, in your Leaving Cert, it could be 3 or 4 decimal places or 2 or 3 significant figures. So always highlighting what exactly it is it's asking you to get your answer correct to. Okay, so one last example of the next type, and then I'll set some questions. So for type 6, we have e to the x equations, where we're asked to solve for x. And here you can see we have e to the 2x minus 8 e to the x plus 15. Now, if you look very carefully at that, what you should notice is that this is a quadratic in disguise. So if I put brackets around this term here in the middle, the e to the x, then I can take this equation and write everything in terms of e to the x. So e to the 2x could be written as e to the x squared minus 8 times e to the x plus 15 equals 0. And now to make it look exactly like a quadratic, we could say, well, let y equal e to the x. And now all of a sudden, wherever there's an e to the x, if I put y, we can clearly see that this is a quadratic that we're used to seeing. Now, when we do this, we have to always be careful that we will solve for y in this quadratic, but we're not asked to solve for y, we're asked to solve for x. You have to make sure you go back at the end and solve for x after we've solved for this quadratic equation. So factors of 15 that multiply to give us 15 and add to give us minus 8 must be minus 5 and minus 3. So if I take out my highest common factor between the first two and the highest common factor between the second two, that gives me y times y minus 5. Minus 3 is common, which leaves me with y minus 5. And these two brackets are again the same, so I can take out my highest common factor a second time, which leaves me with y minus 5 times y minus 3 equals 0. So if I let both of those factors equal 0, then that gives me y equals 5 or y equals 3. So again, we have to say but. If I go back up here, we said that y was equal to e to the x. So we say but y equals e to the x. So that means that if y is equal to 5 or y is equal to 3, then e to the x must equal 5 or e to the x must equal 3. And now we're back to our previous type where we're trying to solve for our unknown variable power, which means I must get log of both sides to do that. So let's take the first equation, and if I get natural log of the left, I must get natural log of the right. I can bring down my power once I have my logs there. And then we should spot the natural log of e, which is 1. And therefore I have my answer, x equals natural log of 5. Now, if we're not asked to write this correct to so many decimal places, then I can leave my answer in terms of natural log of 5. If I do the same for the second equation, e to the x equals 3, well, if I get natural log of both sides, I have natural log of e to the x equals natural log of 3. I can bring down my power using my log rules on page 21. And again, natural log of e is log e to the base e, which is 1. So that gives me x equals natural log of 3. So great use of our log rules to solve for unknown variable powers. So let's have a look at the sheet for some questions. So on the sheet, question 32, 33, 36, 38, then 42, part 2, part 3, part 5, part 10, and 43, part 3 and part 4.